Thank you very much, Alexander, for the nice introduction. And it's really a great pleasure and honor for me to be here today to give a talk on distributed intelligence over wireless networks. So from the beginning, I would like to give a small overview on the evolution of mobile standards and what we are facing nowadays when we look ahead of 6G. So from 1G to 5G, as people know that these mobile standards are usually updated every 10 years. And every 10 years, we have some new application that generate some new type of data. For example, in the past, at the very beginning, it was mainly voice calls. And then we can transmit some text messages. And then we start to be able to use mobile phones to surf the internet. And then because the development of internet and the media technology, and we started to be able to use our mobile phone to almost do everything online, and such as online gaming, shopping, and video calls. And then for 5G, that just appeared around 2020, ideally should be able to support Internet of Things applications, and with special focus maybe to Industry 4.0. So every time when there is a new generation of mobile standards that are updated, it requires a lot of hard work from both academic and industry researchers and engineers to make it to happen. And we are not doing this for fun. We are doing it because there is a demand. So usually it follows. It goes as follows. When there is some new applications, such as text messages, video streaming, social media, and then online gaming, remote surgery. And then those applications generate different new type of data. And then depending on the communication scenario, we will have different new communication requirements, such as data rates or low latency or reliability or connectivity, energy efficiency or timing. And then depending on what is the new what are the new requirements that we are facing, then we come up with new requirements. So for the past few generations, the principle of wireless communications design has always been built upon Shannon's theorems on channel capacity and the Shannon theorem on channel coding. So according to the first theorem, Shannon-Hartley theorem, it states the channel capacity for memoryless point-to-point AWGN channel as the product between the bandwidth multiplied with log2 1+ signal to noise ratio, and then it tells us how many bits per second that can be communicated over a channel within a certain bandwidth. And then according to Shannon's channel coding theorem, if we transmit at a rate that is below the channel capacity, then theoretically there exists a coding scheme that can achieve arbitrarily low error probability. So wireless communication system is usually designed to achieve the maximum number of bits that can be reliably transmitted between a source and the destination node. When shifting from a point-to-point communication link to distributed systems, we will start facing the problems of wireless resource limitations. Such distributed systems may have many different types of architectures, and here I have listed 3 possible structures of distributed systems. First is some server-based system. So we have one node communicating with many distributed nodes. For example, this can be a federated learning system. And then the second case is peer-to-peer communication network. We have a set of nodes that are locally connected to a set of neighbors. And then this can be a distributed control system, for example. And the third case is network with shared medium access. So we have a set of transmitters and receivers that communicate through a common shared access channel. And this can be networked control systems, for example. and the transmitter can be some controller, and the receiver can be some actuators. And for any distributed system that relies on information exchange between a set of users or a set of nodes to achieve some common goal on achieving some performance goals, the wireless connectivity will always be the performance bottleneck in terms of how fast, how reliable the system is, and how fast we can achieve the optimal performance. So as we all know that wireless communication resources can be frequency, time, or space, and existing multiple access technologies such as FDMA, TDMA, or SDMA all rely on the principle of either dividing the communication resources in an orthogonal or non-orthogonal manner. And then the resource allocation design usually follows the objective of maximizing some rate-based metric. So if we consider a wireless uplink with many transmitters sending to a common receiver, and then we have each of the channel have a channel gain GI, and then we can calculate the achievable rate of each link as a function of the channel gain. And then we can set up some optimization function that maximizes either the sum rate of the system or the minimum rate of each of the link. So the first is the maximum sum rate problem, and then the second is the max-min fairness problem, or some other variations of some other metrics that are some minor variations of a rate-based performance matrix. So for 6G, that is ahead of us, if we want to come up with a new wireless design, then we first need to ask ourselves, what will be the new applications that will appear in 6G? And what are the new type of data that are generated by these new applications that will be supported by 6G? And what will be the new communication requirements for this new type of data traffic? So from my point of view, I think we can divide the data traffic for 6G applications into two main categories. The first category is for human perception. For example, if we send some text messages, and then these messages usually carry some specific meaning, so it must be correctly received. And then if we watch some videos online, then having a higher rate requirement is good, because higher rates usually implies higher quality of experience. But for machine, second category is for machine perception. So most of actually all the leading telecom companies has pointed out that 6G would be the era of connected and distributed intelligence. So as compared to the previous generations, this machine perception is really a new application. And for this kind of systems, in addition to having some centralized server that has computing capacity that can process some artificial intelligence tasks, we can also allow the edge servers to have some to be able to process data that are either connected from a different set of devices or data that are generated at these edge servers themselves. And then they can also participate in some machine learning tasks. Or we can have a set of devices, depending on the tasks. It can be autonomous vehicles or some automation tasks, and then some regular phone services or artificial or AR, augmented reality, virtual reality applications. Then we can also have a set of distributed systems that collaborate together in achieving some common goal and solving some artificial intelligence tasks. And in this type of systems, first we realize that this principle of error-free communication that has dominated the research area of wireless communications might not be necessary anymore. And then second point is that performance of such distributed intelligence system will depend on the task that is performed, such as training or inference or control. So which means that we need to come up with new communication design to achieve task-oriented communication. So traditionally, machine learning and some other kind of computing tasks are performed in a centralized server with very large computational capacity. However, training a machine learning model requires a large amount of data, and this data are usually generated at many different user devices. And if we want to upload all the training data to a centralized server, first, it will consume a large amount of communication resources. And second, it also might raise some privacy concerns about the data that we share with a centralized server. So these two motivations has created the development of distributed machine learning with on-device intelligence. And here I have shown two types of architectures that falls in the category of distributed ML with on-device intelligence. And for both this type of systems, the goal is for a group of devices to collaborate in training a common machine learning model, which is parameterized by some d-dimensional vector theta. And then each of the devices will have some local training data that is denoted by SK for the case device. And then we denote S as the entire set of training data in the system. So it's the union of all the local training data sets at each device. And from an optimization perspective, the objective of the system is to find this theta, optimal theta, that minimizes the global loss function that are defined over the entire data set. And then for the figure on the left-hand side, we can apply some parameter server that is in charge of distributing and aggregating the model updates to help this distributed node to learn something in a synchronous way. Or we can adopt another structure that is on the right-hand side. So in a fully distributed system and a node, we can apply some decentralized consensus optimization technique so that the node or the nodes will be able to converge to the optimal parameter vector theta by local training plus information sharing among its connected neighbors. So for the first case on the left-hand side of the previous slide, one example is called federated learning. And federated learning, it has attracted quite a lot of attention in the past few years. And because it shows how communication design can affect the performance of a distributed system. So idea of, and if we apply a federated learning in at the wireless edge, and this is also called a federated edge learning system. So we have some edge servers which can have both computational capacity and transmitting and receiving power. And they will be able to assist the learning process of a set of distributed nodes. And the system follows an iterative process. So it is divided into many iterations, and each iteration is called one communication round. So during the Tth communication round, the edge server will broadcast the current global model theta t to the set of participating nodes. And then each of the devices will perform on-device training, which can be one step or several steps of stochastic gradient descent. For example, calculate the stochastic gradient based on its locally randomly sampled data, SKT, from its own local training data. And then it sends the updated parameter or the difference between the parameter before and after training. So it can either send theta kt or this stochastic gradient vector to the server. And then after the edge server receives the model update from the set of participating devices, it will aggregate these received model parameters by applying some weighted averaging rule. And then it will broadcast the new global model theta for the T+1 communication round. So in such kind of systems, the communication takes place in both uplink and downlink. For downlink, the server transmits, distributes the model to the set of participating devices. And for the uplink, the devices will upload their updated model to the edge server. And this is the part that is mostly affected by resource constraint. So now we will see how does the performance of a federated edge learning system will be affected by limited communication resources. So in a digital communication system, we have source coding for data compression and channel coding for error control, error detection and correction, and digital modulation, converting digital signals to analog signals that will be able to transmit it in an analog channel. And as we have seen in the previous slides, if we transmit information data at a rate that is lower than the channel capacity, then theoretically, we can always find a channel coding scheme that can achieve error-free communication. So that will give us a maximum number of bits per second that can be transmitted correctly over a channel. And this, if we have a system with resource limitations, whether it's frequency limitation or time limitation, according to the channel's channel capacity, if we transmit below the capacity, we can always achieve error-free communication. Then these resource limitations will be eventually translated into limited number of bits. And if we want to share these bits among different users, then that corresponds to limited number of scheduled devices and limited number of information bits per user. And if for the source coding part, if we use some kind of sparsification plus quantization schemes, then each user needs to sparsify and quantize its model updates to fit the limited number of information bits that it is allocated to. Then that will create compression loss in the source encoder part. So here we have an example on how does the user scheduling and resource allocation affect the performance of a federated learning system. We have you consider the system with 100 users, and they collaborate in training a convolutional neural network for classification problem, and we use this MNIST data set for handwritten digit recognition. And we can see we have simulated for both cases with IID data and non-IID data. And we have plotted the test accuracy as a function of the global iterations for the case with selecting different number of users. So if we select more users, then each user will get less quantization bits. So there is a trade-off here. And for both cases, we can see that if we schedule too many users, then the allocated quantization bits for each user will decrease a lot. And then in most of the cases, it's not good to let all the users to participate because the compression loss will be so high that result in very inaccurate aggregated model. So ideally, if we have limited resources, we would like to schedule the users with the most significant impact on the learning result. And we will come back to this point later on to see a few examples on how we can quantify this significance of the model updates. And now we will dive a little bit deeper into this task-oriented communication for federated learning. So as I have seen earlier that when we move from previous generations to 6G, one important part will be task-oriented communication. And then for this particular case with federated learning, and if we consider that the model update is the gradient vectors, then we have a set of users from user 1 until user n, and they want to send their gradient update to the server, and server need to aggregate them. So what is the task here? The task here is to compute the aggregated gradient vector, which is the weighted sum of all the UKs sum over all the devices. And it's also important to notice that these gradient vectors, since they are stochastic gradients that are obtained after calculating the gradient of some randomly sampled data. So the gradient update itself is a noisy measure. Then it tells us that error-free communication in a digital system maybe is not needed here. And the objective, the eventual objective is that in each iteration, the received aggregated parameter vector should be as close to the ground truth GT as much as possible. So instead of using a traditional digital communication design, we can perhaps remove that part and just let all the users to share the same communication resources. And then we will exploit the property of signal superposition in wireless channels. And we can create some kind of a linear mapping between the data values and the received signal amplitude so that we can aggregate the data in a signal level instead of coding and modulation, using the coding and modulation design. And this is also called over-the-air computation for federated edge learning. So with this transmission design, we will not divide frequency time resources to different users. Instead, all the users will share the same frequency time resources. And we will not use the source coding plus channel coding, which are usually non-linear functions. Instead, we will use some linear pre-processing at the sender side and some other linear post-processing functions at the receiver side. And then we'll use analog amplitude modulation so that we can just superimpose the received signal together, and the superimposed amplitude will be proportional to the received, to the weighted sum of weighted average of the model update. And here in this case, the noise, channel noise is directly added to the received superimposed signal. And this noise power and the transmission power limitations will affect the estimation error, which is the difference between the estimated G and the ground truth G. So the theory behind this over-the-air computation can actually be traced back a long time ago to the joint source and channel coding for distributed computation of functions over Gaussian Mach channels. But it is particularly useful for federated learning because in this case, we just want to calculate a simple linear function of the model updates. And in many papers, they have shown that over-the-air federated learning can achieve much higher transmission efficiency with much lower communication delay, especially when the set of participating devices is very large. So from the perspective of distributed optimization, federated learning can be seen just as one instance of distributed and parallel stochastic gradient descent. But why it has appeared again and it has attracted so much attention is because now we need to consider a lot of practical properties when we apply distributed learning or collaborative training in a real physical network. Because first, in a real network, the devices we have the problem of massive devices. So the number of devices can be very high, and those devices can have very heterogeneous computation power. And then second, we might face the problem of non-IID and unbalanced data. And the third problem is limited communication, and especially with imperfect communication. And there are two well-known problems. The first is the structural issue, and the second is the communication constraint. And we will just use one example to show what is the structural issue. So in a traditional federated learning system with synchronous training, the model aggregation takes place after all the model updates are received at the receiver side. So if we have 4 users and each of them have different computation capacity, so some of them will finish the computing task earlier and some will finish later. And then the system will wait. So we have the initial model that is theta 0. And then the system needs to wait until the server receives the model updates from the slowest user, which is user 1. And then it will aggregate the received update and get a new model and broadcast the new model to the set of users. So this user 1 will be the struggler in this case. And this struggler can very much limit the time duration of each iteration of the training process, which is not desired, especially if we have a very strict time requirement. So an alternative way to solve this structural issue is to apply some asynchronous training structure so that users can train their model and send their model updates in an asynchronous manner. So in this case, user 3 finishes computation and sends the model updates, and the server gets a new model and send it back to user 3. And then user 4 will finish its computation and send the new model, and the new updates will be aggregated again, and the server gets a new model theta 2 and then send the theta 2 back to user 4. And this process goes on. So whenever one user or device finishes computation task and it sends the update back to the server, and the server gets a new model, and the new model is distributed back to this user. And we can see that with this updating structure, we will create very heavy communication load in both uplink and downlink, because within the same iteration as one global iteration as in the synchronous federated learning case, here we actually need to update and distribute the model 6 times more. So instead, we propose an asynchronous federated learning framework with periodic aggregation. And the key idea goes as follows. We'll divide time into some fixed length durations t. And then within each duration t, we'll collect all the model updates that are already available. And this user 2, 3, and 4 will send the ready to send model updates to the server, and the server will aggregate them and get a new model and send a new model back to them. But in the meanwhile, device 1 and device 2 and the device 2 will still continue. Device 1 and 2 will still continue their computation until they finish their computation task within the second time duration. And then in this time interval, we get 4 updates. So the 4 updates are sent back to the server, and the server aggregate these 4 updates and get a new model and send this new model back to all of them. And then they will continue this process again. So by using this design, we can ease the structural issue without consuming too many communication resources. But then we have another problem here, because, for example, in the second iteration, global iteration, user 3 and 4 are computed, their gradient updates are computed based on previously received model theta 1, but the user 1 and 2 will upload their gradient vector that are computed based on previously received model theta 0. So different users might have a different age of a previously received global model. And the solution that we have is to apply an age-aware aggregation policy to balance the freshness of model updates. And this is inspired by a notion and a metric called age of information. So the system model that we consider is as follows. We have a federated learning system with n devices that trains a shared model theta. And we have each user device K has a local data set SK, and the entire data set is the union of all the local data sets. And the objective is to minimize the loss function, which is the sum of all the sample-wise loss function over the total number of samples. And then we can also define a local loss function as a loss function that is calculated based on the local training data at each device K. So the training procedure goes as follows. The first step is initialization. Then the server broadcasts the current model to the set of devices. And then the devices will perform local training by applying several times of local SGD with different previously received global models. Then after local training, we have a set of devices that are ready to send their update. And then we will apply a scheduling rule that only schedules a subset of the devices to upload their model updates. And then those scheduled devices will upload their model updates, and they will be aggregated at the server side. And we have applied several scheduling and aggregation designs. First, for scheduling policies, we considered random scheduling, which means that we just randomly select a certain number of users among all the available ready-to-update users. And the second policy is called significance-based policy, and it is proposed in this paper in the footnote. And the idea is that we choose the ones with the largest L2 norm of the gradient update vectors. And then the third policy is frequency-based. We choose the ones that have been less frequently scheduled in the previous round to balance the participation ratio of each devices. And as for the aggregation part, we also apply different type of aggregation designs. First is equal weight. We apply equal weighting factor among the users. And then the second policy is age-aware weighting design. We define the age of local updates as the difference between the current iteration T and the previous global iteration where user K has received a model. And we can apply a weighting design to allow the weight to grow or decays exponentially with the age of local updates. So if we put the weight to grow with age, then we will be favoring the updates with an older age. And if we apply a weight that decays exponentially with the age of local update, it means that we will prefer to put higher weight on fresher update. And here is the simulation result that we have obtained with the MList dataset. We have 100 users in total, and in each iteration we can schedule at most 30 users. And this case is for the case with the IID data distribution. So every user have the same data distribution that covers all the digits. And then we also consider the training time to be very heterogeneous among different users. And then we plot the test accuracy as a function of the global iterations. And we will see that actually random scheduling as the blue curve is the one that is on top. And the F fresh means that we use an age-aware design and with a gamma that is smaller than 1, so meaning that we favor fresher model updates. And we can observe that this policy has this age-aware aggregation policy can achieve much better performance as compared to the baseline federated averaging algorithm. And we also see that for this type of significance-based scheduling here actually performs not as well as random ones. And for the case of non-IID data, we observe that if we apply a significance-based scheduling, we'll have a lot of variations across the iterations on the test accuracy. And then similar to the previous case, if we apply a random scheduling plus with the age-aware design that favors fresher model updates, we can get a much better performance as compared to the other ones. So from these results, we actually observed that random scheduling performs surprisingly good as compared to the alternative, but we need to, especially in the asynchronous setting, we need to use some kind of weighting adjustment to compensate for the different age of the age values of the received update. And we have shown that, especially if we consider an age design that prefers that favors the fresher updates, we can achieve better performance than the alternative solutions. And at the end, I would like to mention that as a research direction, so wireless distributed intelligence over wireless networks lies within the intersection between these following 3 areas: machine learning, distributed algorithms, and communication theory. And there are many different aspects that can be explored, such as resource allocation and semantic communication, which is actually includes the task-oriented communication design that I have just briefly talked about, and cross-layer control. So we cannot just limit ourselves to physical layer resource allocation. We also need to combine different layers such as physical layer, MAC layer, and network layer, and to come up with joint design to support the functions of distributed intelligence systems. And signal processing and fault tolerance, which shows how resilient the system is against either faulty parties or adversarial attacks, and privacy and security, which contains both privacy aspect of data and security against, for example, physical layer attacks. So there are a lot of topics and directions that can be explored under the umbrella of distributed intelligence systems, and I will be very glad to discuss further about this topic with you. And this is all I have for today. Thank you for your attention.